friends, how are you? Actually, I made this intro. Hope you like it. Please don't forget subscribe and share. And now let's go.
Guys. We have here this question. Let's read it. The two events A and B are independent with P of A 0.1, P of B 0.05. So compute the probability of A bar enter B bar. Is it easy? See you guys, it's easy. Because A and B are independent, this intersection will be equal to P of A bar times of P B bar. Because A and B are independent, we use this rule. Fine. P of A bar. What? Wait. Very good. P of A bar is the complement of PA. And P of B bar is the complement of PB. So they are 1 minus P of A times 1 minus P of B respectively. Fine. So 1 minus P of A times 1 minus P of B equal 1 minus 0.1 times 1 minus 0.05 equal to 0.855. Guys, I'm really sorry. This question is not easy. Well, you may pay attention. Okay? We can do it, but please, you must pay attention. So let's see what it is. Assume that the probability that a born baby is a boy is 0.5. Well, and that the gender independent between births. Okay. A family has 4 children. Great. Compute the probability that they have 2 boys and 2 girls, conditional that. So knowing that the first means the oldest child is a boy. Look it. It's not simple at all. But yes, guys, we will solve it. Me and you, as a one hand, we can solve this question. So guys, let's do it. Here we know that the first birth is a boy. So we now interested only in the gender of the second, third, and fourth births. And we want these births to be 2 girls and 1 boy. So in results, we have 2 girls and 2 boys, because we have already the first child as a boy. Well, first, in how many ways can the birth of the 2 girls and 1 boy be arranged? Before, let's take a look of this word. Dad. Daddy. Dad a word of 3 letters. In many ways can these 3 letters in this word be arranged? Well, it can be D-A-D or D-D-A or A-D-D. We have only 3 ways. So the rule of this arrangement is, let's write here, 3 factorial over 2 factorial. What? I'm gonna tell you why. 3 factorial because we have 3 letters. D, A, D. So 3. Over 2 factorial because we have the letter D twice. So the letter D is repeated twice in this word. So the rule will be like this. 3 factorial over 2 factorial. And it's equal to 3. Well, this is a way and this is a way. 3, 3. Now, let's go back to our question. The probability that this beautiful family have 2 boys and 2 girls, knowing that the first one is a boy. Well, the probability of having, let's write it, okay? Let's just write it. Of having 2 boys and, this is and, 2 girls, knowing that, condition of that, the first child is a boy. Let's write it like this. As the first birth is a boy. Well, equal. Well, having a first child as a boy is already occurred. So we still have to know the probability of having the remaining boy and the 2 girls. So, having these 2 girls, and we can spread it like GG, 2 girls, and this boy, well, this is equal to, let's write here, equal to half for having a girl times, or having another girl, it's a half, times having a boy, another birth, half, but times 3 factorial over 2 factorial. And it came from the arrangement of the births of the 1 boy and the 2 girls as the word dad. Fine. So we have this one as a first birth, and we can having a girl in the second birth or a boy. So we can, let's write it for more details. So I can have for a second birth a girl, third birth a girl, fourth birth a boy. Or the second birth can be a boy, the third one girl, and the fourth girl. Or the second can be a girl, the third one boy, the fourth one another girl. I'm sorry. Well, is equal to 3/8. But this question isn't finished yet. We have another part here waiting us. We should calculate the probability that they have 2 boys and 2 girls, knowing that at least one is a boy. Let's write it. Probability of having 2 boys and 2 girls, knowing that at least one is boy. Fine. So how we can solve this probability? Hey you guys, what about the conditional rule? Let's try it. Probability of having 2 boys and 2 girls. Enter having at least 1 boy over the probability of having at least 1 boy. Is it cool? But first, let us know. At least 1 boy. What does it mean? Well, having at least 1 boy means that we can have 1 boy and 3 girls, or 2 boys and 2 girls, or 3 boys and 1 girl, or 4 boys. Now, what is the intersection between these 2 events? Having 2 boys and 2 girls, and at least 1 boy. Hey guys, where is this intersection? Here. This one. So, this is the probability of 2 boys and 2 girls over the probability of at least 1 boy isn't the complement of 4 boys. Well, the event at least 1 boy is the complement of the event having 4 boys. So I can put it like 1 minus the probability of having 4 boys. Okay. So it's equal having a boy half times having another boy half times having girl half times having another girl half times what? Well, pause the video and think about it. After pausing the video, I can say that is 4 factorial over 2 factorial times 2 factorial. So it's the same idea here. But why 4? Because here we have 4 children. And we want to arrange them in different ways. Boy, boy, girl, girl times 4 factorial over 2 factorial because we have 2 boys times 2 factorial because we have 2 girls. Same here. Fine. Oh, this is a big fraction here. 1 minus the probability of having 4 boys. Same here. We can know that we have here 4 children. Well, as here. So each child has a half of probability. So 1 minus half times half times half times half. So 4 times, it's 1 over 2 power 4. Well, all of this give me just 0.4 as a result.
That's all for today, you guys. Please stay ready and we'll meet very soon. Don't forget, subscribe and share. Goodbye.